All right, so today let's talk about the periodic table and a little bit of the history behind chemistry and the periodic table. So the periodic table, as you know, is one of the most recognizable symbols for chemistry and in science in general. Most people probably know if you show them a picture of the periodic table what it is. They don't know what to do with it necessarily, but they know that it is a chemistry thing. And indeed, this is one of the prettiest visualizations that we have around in physical sciences. And it came to be around the late 1800s, right around the time that chemistry kind of solidified as its own branch of science. And it sounds like a long time ago, like 120 years ago, 150 years ago, whatever. That is when chemistry kind of came to be its own thing. Yes, it was a long time ago, but when you compare it to other sciences, it's fairly new. First of all, chemistry is newer than the United States. Think about that. And second, physics and biology, well, they've been around since humanity started. People have been thinking about balls going down hills and ailments inflicting one another since the time of ancient Egypt or something, right? So you can ascribe the term physicist or biologist to a whole bunch of different people throughout history. Chemistry was not really a thing. The closest thing to it was alchemy, not really chemistry. So understanding chemistry really came to be around the time of the Industrial Revolution, and so it's pretty late in the game that we're talking about here. Anyway, the person who recognized that we can actually organize atoms in increasing sizes of weights was Dmitry Mendeleev in the late 1800s, and this is basically what he did. He organized them in increasing weights like this, and he puts them in periods and groups. He called every row a period and every column a group. And he noticed that when he did this, all the groups, all the constituents of a group had similar properties, and he thought that was pretty cool. And he also noticed that there were gaps of the known elements. So he saw that there was a huge gap between 40 and 48. He's like, there's a hole here. We're probably missing an element. I predict that one day something will be found between calcium and titanium. Okay, and he was right. We found a bunch of different things, not necessarily there, but we found a bunch of different things where he predicted there would be holes, where we didn't know that element at that time, and then we discovered it later on. And This is his actual, in Russian, version of the periodic table. It's exactly the same thing as this turquoise thing here, just in Russian. As you can see, he has some holes, he has some mistakes, but the idea is, the correct skeletal structure is there. We still have lithium, beryllium, sodium, magnesium, potassium, and calcium exactly where he said they'd be, and we still have increasing the atomic number as he predicted there would be, and he put holes where he thought some more should arrive that didn't exist yet. Okay, and he also thought that hydrogen could count both as a nonmetal and as a metal, so he didn't know where to put it, so he double put it. So that's kind of cool that he was able to do that. And indeed, we did find some stuff that he thought didn't exist yet. Okay, so that's enough history. Let's talk about what we could do with the periodic table. We talked already about the electron configuration. We could use the periodic table to help us guide us to find what electron configurations are for different elements. Another thing we could do with it is predict physical properties for atoms. So here's one thing, the size of an atom, and we'll call that the atomic radius. So it's the same thing as in math. It's the radius of a circle. So if I have this pink thing here as the atom of whatever you want, the radius for this thing would be the distance from the center, the black circle here, to the edge. The problem is that atoms don't have clearly defined edges, right? So the way physicists and chemists actually measure it is they actually look at the center, which was the nucleus is, so it's easy to find, the center of one atom and the center of another atom that's hanging out with it, like maybe they're bonded, and they measure the distance between the two centers, and they say if we divide it in two, that's the radius. Because as you remember, S and P and D and F, they're not necessarily circles, and they have different cloud shapes, and they're very funky looking, so we don't really know how this necessarily looks. This is how we'd measure it. All right, don't worry too much about it. You're not going to measure it yourselves. I just wanted to tell you what that is. All right, so when I'm looking at the periodic table, as I go leftward within a period, I'm increasing the size of my atom, and as I go down a group, I'm increasing the size of the atom. And I have another visualizing thing here for you. The height of each one of the boxes corresponds to the size of the radius, so the size of the atom. And you can see this really does track as we're saying. As you go down the left, things increase. So if you go down, say group number one, hydrogen would be the smallest, and cesium here would be the largest. They didn't measure francium, so cesium would be the largest, and that's exactly what this thing shows you. And you can see it's generally true, but the green guys here not as much. But for the other atoms, pretty good bet that if you follow this rule, you'll be able to organize atoms in increasing sizes. So what can you do with this? All right, let's use a periodic table to arrange the sizes of 3 random elements and see if we can do that. So aluminum, carbon, silicon. Let's zoom in on where they live because we don't need the whole periodic table for that. And I want to know which one's the smallest, which one's the second smallest, and which one's the largest. Okay. So if I look at carbon and silicon right here, I know that as I go down a group, I increase the size, meaning the carbon is smaller than silicon. So already I know that C is less than Si. Okay, so I already figured that out. Now let me compare silicon and aluminum. I know that as I go down to the left within a row, I will also increase the size. Okay, so I know that silicon is smaller than aluminum. So since this is smaller than this and this is smaller than this, I can organize it this way. Carbon is smaller than silicon, silicon is smaller than aluminum. Okay, and you can kind of generally do that for any 3 or 4 whatever elements as I give it to you. That's a classical question to ask about atomic radii. So let's talk about the ionization energy. The ionization energy is the energy that's required to remove an electron from an atom. And basically, as you know, every atom has a certain number of valence electrons, and you can start removing them. But removing an electron is not necessarily something that the atom would want to do. It belongs to it. If you have to pay it some to take it. So some atoms would require more of a payment in exchange for that electron. All right, and that payment is, we call that the ionization energy. The first ionization energy is the first electron it wants to give you. The second ionization energy is the second electron it could give you. So right now I'm talking about the first ionization energy, the energy required to take the first electron away. All right, and let's think about sodium and magnesium. So you can go ahead and pause me and try to think to yourselves. If this was a regular classroom, I would ask you right now, I would ask people to volunteer and tell me what they think is would have a higher ionization energy, sodium or magnesium. So sodium has this electron configuration and magnesium has this electron configuration, meaning that sodium, if it lost 1 electron, it would look like a noble gas. Magnesium, if it lost 1 electron, it would not look like a noble gas. So you bet sodium would want to lose its electron more readily than magnesium because sodium would look like a noble gas, which is stabler. If it lost this and became 3s1, it would look like a sodium, so it's still not as stable as a neon. So it would have a higher ionization energy. That's what I would predict. And yeah, that's exactly what we see. As this is the opposite of the atomic radius. As you go to the right, within a period, you increase the ionization energy, and as if you go up within a group, you increase the ionization energy. So if we're looking at sodium and magnesium, yes, magnesium is larger than sodium. And let's try to organize argon, selenium, and sulfur in order of increasing ionization energy. And let's zoom in to where they live. I have argon here, I have sulfur here, and I have selenium here, and I have the behavior here copied here. Okay, so I'm going to look at argon and sulfur. So within a row, within a period, as I go to the right, it increases, meaning that argon is probably larger than sulfur in ionization energy magnitude. And so I'll say that argon is larger than sulfur. And as I compare sulfur and selenium, sulfur should have a higher ionization energy than selenium based on this trend of increasing going up. And so indeed, this is what I would get. Selenium would be the smallest, followed by sulfur, and argon should be the largest. This makes sense because why on earth would argon want to give up any of its electrons? It's already the stablest it could be. So argon is pretty stable and happy, so it wouldn't want to do that. All right. Okay, let's talk electronegativity. It's another physical property that these atoms would have that you can predict using the periodic table. It basically measures how an atom can attract electrons to make itself a negative ion. All right. So if an element doesn't want to become a negative ion, it would not have high electronegativity. Have a low electronegativity. If an atom wants to be a negative ion, in which case it would become like a noble gas, then it would have a high electronegativity. So try to think to yourselves, which one do you think would have a higher electronegativity, sodium or fluorine? And you could look at the periodic table here. Fluorine is up here, sodium is up here. Okay, so pause for a second and think. All right, fluorine, if it gets an electron and becomes negative, it would look like neon. Sodium, if it gets an electron and becomes negative, it would look like magnesium. So why would sodium want to do that? Sodium wants to lose the electron, not gain one. Fluorine, yeah, it wants to get that electron. So fluorine is going to be much more electronegative than sodium. Okay, so group 7, as we just showed, really wants that extra electron to be stable. Group 1 really doesn't want it. Okay, and this trends the exact same way as the atomic radius. Because smaller atoms get to attract electrons more easily because the nucleus is much more easily exposed to any electron that's coming around. And I'm showing you here the table. This is a periodic table of electronegativity from Wikipedia. I believe, this is from Wikipedia. This is a pretty good estimation here. They omitted the noble gases because they don't really want to get electrons. They're pretty happy. And you can see sodium is much, much lower than fluorine. Fluorine is actually the highest. And it trends the same as atomic radius, meaning going up, we increase, going to the right, we increase, just as we saw before. And I can ask you exactly the same kind of type question about electronegativity. I won't. It's the same idea. So we already went through 2 examples. Let's talk about electron affinity. Okay, this doesn't measure how much they want to become negative ions. It measures the energy change when you add an electron, okay, to a gaseous atom. Right, so similar-ish, but different definition here. Now we're talking about an energy. Here we're talking about propensity, or what they kind of want to do. All right, here we're talking about energy, that you can actually measure this energy. All right, and like I said, it's a nuanced version of electronegativity, and it does not take the size into account. It just takes the energetics into account. All right, and you can see here the energy associated for these guys compared to these guys. Right, so group 7A would have the highest, and group 8A would be the lowest, and group 1A following that too. So that's the electron affinity. All right. Metallic character, as you'd imagine, the farthest you are from nonmetals, the more metallic you would look. And what I mean by metallic character is how typically of a metal does this atom act. So some metals don't act like typical metals. Like, when you think about a metal, for example, you think of something that's, for example, very heat conductive, meaning that it gets hot very quickly and it doesn't insulate very well, right? Aluminum, you probably know that from your own experience. If you put aluminum in the oven, you take it out, 3 seconds later you can touch it. If you took iron, which is one of these macho metals, you put that in the oven, take that out, you can't touch that for quite a few minutes. All right, so that's much more in line with what you would imagine an atom of metal would look like, whereas aluminum having less of a metallic character wouldn't act that way. Obviously, fluorine would act a lot less as a metal compared to any of the actual metals. So it would trend this way. Going to the left, you would decrease. Going down, you would decrease. You would increase. Sorry, going to the left, you'd increase. Going down, you would increase the metallic character. This denotes how you increase the metallic character. More metallic, more metallic, more metallic, more metallic, more metallic, more metallic. Right? And that's about it. So hopefully this made sense. Let me know if you have any questions.